and the scan rate through Randall-Savick equation. This is a very useful equation in cyclic voltammetry. Okay, here as you can see, the peak current is directly proportional to square root of scan rate and directly proportional to square root of diffusion coefficient, and also directly proportional to number of electrons and concentration of the species. Okay, as you can see, this equation is like y is equal to mx form, you know what we studied probably in school, where if you plot y versus x, let's say ip versus nu power half, you would get a linear relation, you would get a linear plot that passes through origin. Maybe I will have that. Yeah, so you would have a linear relation which passes through origin. Okay, so by looking at the slope and by using this Randall-Savick equation, one can determine the number of electrons involved in the process if we know the diffusion coefficient, or if you know the number of electrons, you can determine the diffusion coefficient. Okay, so that's why this technique is a very powerful technique. Remember, when you keep on changing the scan rate, as you can see that the peak current increases both in forward as well as in reverse directions. Okay. Now, the formation of peaks in the forward and reverse scan alone is not a criteria to assess that the given process. The given process is a. Okay, I missed a slide. I think. Okay, it doesn't matter. Okay, the formation of peak both in the forward and the reverse scan alone is not a criteria to assess that the given electron transfer process is a single electron reversible process. There are 6 different diagnostic tests one has to follow. The first one is the peak-to-peak separation between the forward and reverse scan is about 60 millivolt, 59 by n millivolt. For a single electron, it is 59 millivolt. Okay, so that's the Nernstian relation. And similarly, there are 6 different diagnostic like peak current for both cathodic and anodic process should be same, and IP is directly proportional to nu power half, etc. You know, you guys can always read a book called Instrumental Methods of Analysis. Okay, Instrumental Methods of Analysis in Electrochemistry. There is a book by Southampton group of people. A lead author is K.N. Bartlett. It is P.N. Bartlett. Okay, so that book is a good book to understand the techniques. Now, using cyclic voltammetry, one can assess reversible, irreversible, and quasi-reversible process. You can depends upon the electron transfer rate constant. You can see that for a typically fast electron transfer rate constant, you would get a very sharp peak in cyclic voltammetry. The moment you observe that the peak is drawn out, meaning a broad peak, the electron transfer rate constant decreases, and also the peak potential shifts in the positive regime. Okay, so these are some of the kind of information one can derive from cyclic voltammetry. Not just a reversible process, you can also assess irreversible process, and these are the diagnostic tests for irreversible. The complete irreversible process would display only peak in one direction. There is no reverse peak. Okay. Similarly, there are diagnostic tests one can follow, and also apart from reversible and irreversible, you can assess quasi-irreversible process by following this diagnostic test. Okay, so these are some of the valuable information one would get from cyclic voltammetry technique. The many different processes, what I explained for a general concept like diffusion, adsorption, etc. You can analyze electron transfer reaction, right, and diffusion using cyclic voltammetry. Apart from this, one can also analyze the adsorption process which occur in any kind of electron transfer reaction. In such case, okay, in case of adsorption, you would see that the peak-to-peak potential between forward and reverse scan is 0, meaning delta EP is 0. You will see peak formation both in forward and reverse direction at the same potential. By integrating the peak, you would get a value of charge. By measuring the charge, you can determine the surface coverage of molecule using this formula. Lambda is equal to Q by N of A. Okay, so that's the kind of advantages one can get. You can determine the surface excess, surface coverage, etc. by looking at the peak current and correlating with this phenomena. So not only that, you can also assess the cleanliness of the electrode surface. I'm sure whomever is doing PhD in the field of electrochemistry, they normally polish the electrode surface, and it is very difficult to get the reproducible result. I do understand, but how do you get the reproducible result? Only through polishing the electrode uniformly. And you can also polish not just by mechanical polishing, you can also do an electrochemical way of polishing using a cyclic voltammetry. You can run a CV in an acid medium like sulfuric acid, HCl, perchloric acid, nitric acid, etc., so that you would get a reproducible surface. The typical behavior to assess the cleanliness of platinum electrode is by observing this kind of peaks. Okay, so this suggests that if you do a cyclic voltammetry experiment in sulfuric acid, you would typically observe hydrogen adsorption and desorption peak on platinum electrode. By integrating the charge associated with this peak, one can able to assess the surface area of the platinum electrode. Maybe I will talk about this when we discuss electrocatalysis. Okay. So not just the electron transfer processes and adsorption, diffusion, etc. One can also assess metal deposition, nucleation, overpotential, etc. Using cyclic voltammetry. Okay. So maybe due to lack of time, I will skip few slides. But if anyone is interested, always you can post a question in the chat box, or you can ask me the question later. Okay. Now, so in the series of techniques, we discussed about potentiometry, amperometry, linear sieve voltammetry, and cyclic voltammetry. And in the case of voltammetry, the another well-popular technique is pulse voltammetry. There are different techniques which come under pulse voltammetry, like normal pulse, reverse pulse, differential pulse, square wave voltammetry, staircase voltammetry, etc. Why do we apply pulse? It is very simple. These kind of pulse techniques are very much popular in the field of sensors, biosensors, electrochemical sensors, etc. Why do I highlight these techniques in energy? Is because you can able to tune the material characteristics. Okay, let's say if you do a simple electrode deposition process, you want to prepare a size and shape controlled nanomaterial that could be used for energy conversion and energy storage application. Normally what do, you go to a hardcore wet chemical method or some template assisted method, or a hydrothermal method. You use a high temperature technique to prepare such material. But I can suggest that even electrochemical technique could also be used to prepare such kind of size and shape controlled material. How do you control the growth? You can control the growth using this pulse technique. That's the advantage of this technique. Okay. By I hope you guys know what do I mean by pulse. I remember yesterday I talked about it in case of amperometry. What you do is you can apply the staircase kind of input signal, meaning you can vary the potential with respect to time, like on and off, and you can see overall we have a linear ramp, linear variation of potential with respect to time. So this is a kind of digital voltammetry waveforms. The width of the pulse is nothing but your time duration. About that time only you want to apply a pulse. Then you switch off, then go back to another potential and apply a pulse, etc. So that you can control the growth both in terms of size and in terms of shape. Okay, so that's the kind of staircase voltammetry one can apply in case of pulse voltammetry. Of course, these techniques were developed in the early 1960s. It's precisely between 50s and 60s by Sir Geoffrey Barker in UK. And later on, these are modernized like square wave, differential pulse, etc. by Janet and Bob in US. Now, what is the basic behind all this pulse technique? Remember, in case of electrochemistry, it is very difficult to distinguish Faradaic and non-Faradaic process. What do I mean by Faradaic and non-Faradaic process? You guys would know. Faradaic process involves charge transfer reaction like electron transfer rate constant or charge transfer processes like proton transfer, etc. Non-Faradaic process involves no charge transfer, meaning typically the double layer formation, and there could be simple adsorption and desorption of ions. This becomes very critical in case of analyzing electron transfer rate constant. You need to distinguish between Faradaic and non-Faradaic process. How do you distinguish that? You can use a pulse method. Yesterday I mentioned, I remember, but I will correlate again. The non-Faradaic decay is very fast. Okay, so this essentially contributes to e power 1 by 6, t power 1 by 6. That's a very fast decay process, non-Faradaic process. In contrast, the Faradaic process undergoes very, very slow decay. The time constant would be t power 2 by 3 of the order of 2 by 3. So the moment you apply pulse, initially there is a fast decay, non-Faradaic, and the moment it stabilizes, kind of reaches a steady state, you can get a pure Faradaic measurement. That's why by looking at the output, you can able to distinguish both Faradaic and non-Faradaic process in electrochemistry. This is a kind of normal pulse one would apply. You can apply typically varying potential with respect to time, and you can have a rest period. That's where you give the material to grow in terms of controlling the size and shape. Okay, the typical output again in case of pulse voltammetry would be the plot between current versus potential. You would see a typical S-shaped voltammogram. Okay, so this is the current you would measure, and that current is called a limiting current or steady state current. What do I mean by that? Similar to voltammetry technique, the moment you vary the potential, there would be a change in current due to electron transfer reaction. This current value increases because of the increased concentration gradient. But the moment you reach the peak in terms of current, the process is no longer controlled by diffusion. It attains the Nernstian equilibrium, though you vary the potential. Because of the pulse technique, you would always maintain the Nernstian equilibrium, and that's why you get a typical steady state current. Okay. Now, so similarly, maybe I would skip few slides because I want to cover many things today. Let's see how far we go. Okay. So depends upon the input signal, you would get the corresponding output. See, for example, in case of differential pulse voltammetry, you can differentiate the voltage with respect to pulse. As you can see, the fixed linear ramp over which you apply a pulse, and compared to this normal pulse, a differential pulse voltammetry gives you a sharp peak shaped voltammogram as an output, so that you can clearly get the peak current, maximum current due to the electron transfer reaction. Similarly, instead of differential pulse, one can apply square wave, etc. So this is the kind of output signal you would get. In case of normal pulse voltammetry, you would see like an S-shaped voltammogram as an output. But in case of square wave or differential pulse voltammetry, you would get a typical peak-shaped voltammogram as an output. This is a much better technique where you can get a better resolution and better sensitivity, right? So these are the kind of inputs and typical output in case of pulse voltammetry. You can see normal pulse, a differential pulse, square wave voltammetry, and this is a kind of similar to linear sea voltammetry, etc. Staircase voltammetry. Okay, so these are of course the deduction limit, meaning That's the kind of if you want to look at in terms of material growth for energy conversion or storage application, you can use this pulse voltammetry technique by using a very lower concentration of the molecule. You don't have to use like millimolar or molar concentration. So that's the advantage you would get in terms of pulse voltammetry. Now, in this series, we have what is called the electrochemical impedance spectroscopy. Okay, this is the most powerful technique in electrochemistry. Just give me a minute. I hope you guys are listening to me, right? Today I'm talking too much of subject, no story. So let me continue. Okay, you guys are listening, right? You are not sleeping, I guess.
No, sir.
No, you are listening. Okay.
We are listening, sir.
Okay, good. Yeah. So, among the many different electrochemical techniques, electrochemical impedance spectroscopy is the most powerful technique in electrochemistry. Why do we call this as a spectroscopy? Is because there are many controversial arguments for this, but keep it in mind that, for example, in case of spectroscopy like IR, UV vis, NMR, etc., you observe a peak formation and correlate directly to the functional group present in the molecule, directly to structure of the molecule. So similarly, the output in impedance spectroscopy could be directly correlate with the structure of the electrode-electrolyte interface, which is very critical. You can pinpoint some of the elements like resistor, capacitor, inductor, Warburg impedance, etc., so that you can directly correlate the structure of electrode-electrolyte interface. So that's why electrochemical impedance spectroscopy is a very powerful technique. Maybe I will spend definitely about 10 minutes because this is very critical. Now, what's the basic principle behind this technique? This comes under AC technique. In this technique, what do you do is, you fix the DC potential. Okay, you fix the DC potential. That DC potential could be your open circuit potential, E0 or E half or equilibrium potential. You get me? It could be open circuit potential, it could be E half, it could be equilibrium potential, or it could be E0. All these things have meaning. Hopefully you guys would understand that, right? So you fix the DC potential over which you superimpose a sine wave of peak to peak. Okay, that's the amplitude of the signal, over which you superimpose a sine wave of peak to peak difference roughly about 5 to 10 millivolt. Okay, only in the case of corrosion you observe a large perturbation of 50 to 100 millivolt. Otherwise, you need to apply only about 5 to 10 millivolt. Why we need to apply such a minimal perturbation is because you can directly correlate the system to equilibrium. Okay, because at equilibrium the system exhibits its real characteristic. That's why you apply a very minimal perturbation. So you apply a sine wave of very minimal perturbation. That's the kind of input perturbation, potential versus time. And since you apply a AC sine wave, the output will also be of sine wave. Okay, it's like this. And you look at the output signal in terms of change in amplitude, meaning peak height, change in amplitude, or the change in phase shift. That could be directly correlated with the impedance. Since you apply a AC perturbation signal, the resistant in this case is called impedance, and the impedance has both real and imaginary part, Z prime and Z double prime. The change in amplitude is directly correlated with the real part of the impedance. Okay, and the change in phase shift is correlated with the imaginary part of the impedance. And in terms of electrical circuit element, the real part of the impedance is directly correlated with the resistance alone, and the imaginary part of the impedance is correlated with the capacitance and the resistance and capacitance combinations. I will get back to this point. Okay, just to remember this, the peak to peak amplitude change is directly correlated with the real part of the impedance, and the change in phase shift is correlated with the imaginary part of the impedance. Now, since you apply again the AC perturbation signal, there is a time constant associated with this process. You can change the frequency. What do I mean by frequency? Frequency is 1 over hertz. Okay, it is inversely proportional to time constant. Normally, in case of impedance spectroscopy, you can vary the frequency from megahertz to microhertz. Now, we do have instruments through which you can vary between 7 megahertz to 1 microhertz. So you can imagine megahertz to microhertz, 10 power 12 orders of magnitude one can change. That's why this technique is very powerful. 10 power 12 orders of magnitude change. Okay. Now, so by changing the frequency, what do I mean by changing the frequency? When you vary between microhertz to megahertz, what you do is you apply a similar kind of sine wave. Within this half wave, you can apply one more sine wave, like one more sine wave even within that half. So that's the meaning of changing the frequency. So for each of those perturbation signal, you would get the corresponding output signal in terms of variation in current with respect to time. So if you look at such kind of output, it would be a complete chaotic, and you will not get a meaningful information by looking at the output in impedance. I hope you understand what do I mean by that, right? By changing the frequency, you are going to apply within this half signal one more sine wave, and within that half one more sine wave like this. So for each of those perturbation, you would get the corresponding output. So it would be very difficult to get a meaningful information by looking at output in impedance like this way. That's why the output in impedance spectroscopy is expressed in terms of two different plots. First one is Nyquist plot and the other one is Bode plot. Okay. So the Nyquist plot is a plot between Z real and Z imaginary. And the Bode plot, again, we do have two different categories. One is a Bode frequency plot, where the total impedance is plotted against the log of frequency. And in the other kind of Bode plot, where the phase angle change is plotted against the log of frequency. Okay. So these are the typical output in impedance spectroscopy. Now, in case of Nyquist plot, okay, you go from a high frequency measurement to low frequency measurement. You start from megahertz or kilohertz to microhertz or millihertz. Okay. Suppose, let's say, you observe in case of a Nyquist plot, a small semicircle and a straight line. Okay. The formation of semicircle indicates the process is controlled by charge transfer. Okay. Kinetically controlled process. And the formation of a straight line at low frequency indicate that the process is controlled by diffusion, mass transfer controlled process. Suppose if you don't see any straight line, if you see a complete semicircle in impedance, then that indicates that the process is controlled by charge transfer process, completely a kinetic controlled process. Now, remember, I used to take impedance at least 2-3 hours in class. I am trying to squeeze that in within 5 to 10 minutes. So there would be a fast way of communication. But if you can listen to me, at least I will try to highlight the importance of this impedance spectroscopy. Now, the very first point of highest frequency of your measurement is called the solution resistance, which is RS, or uncompensated solution resistance. Okay. And if you fit that into a semicircle, the second intercept on the x-axis is RS plus RCT, meaning charge transfer resistance. What do I mean by charge transfer resistance? The resistance offered by the electrode towards any charge transfer process. Okay. The resistance offered by your electrode towards any charge transfer process is called RCT, and the difference between these 2 points will give you the value of RCT. And in the field of corrosion, They call this RCT as RP, polarization resistance. The resistance offered by the electrode towards polarization process. Okay, and the Z double prime maximum could be used to measure directly the capacitance. Z double prime maximum is equal to 1 over omega c. Omega is an angular frequency. Omega is equal to 2 pi f. F is the frequency you apply between kilohertz to millihertz, megahertz to microhertz, etc. So omega is angular frequency, 2 pi f. So by measuring the Z double prime maximum, one can directly determine the capacitance of the electrode surface. Okay, so that's why by looking at impedance spectroscopy, the output in impedance spectroscopy, one can directly correlate with the double layer structure. I'll come back to that structure. Okay, you can measure directly the uncompensated solution resistance, double layer capacitance, and the RCT. Suppose if you have a straight line at low frequency regime, that corresponds to mass transfer process. It arises because of the resistance to diffusion process. That is represented by a parameter called Warburg impedance. Warburg is W. Okay, Warburg impedance. So how do you distinguish this between a straight line for a diffusion and a capacitive behavior? In case of diffusion, the phase angle should be 45 degree and the slope of this line should be unity. That's how you distinguish between the straight line due to diffusion and capacitance. I'll come back to this point a bit later. Right now you assume that there is a small semicircle and if it is straight line, and this the kind of equivalent circuit one would fit to determine the parameter. Okay. Now, why do we do electrochemical impedance spectroscopy measurement? Okay, so this kind of spectroscopy impedance measurement arises because of the need to understand very fast electron transfer kinetics. As I mentioned, you can vary 10 power 12 orders of magnitude of change so that you can able to understand many different processes, starting from corrosion, adsorption, desorption, even material characteristic like conductivity,